Not.
Okay, so experiment time.
Yes. So let's explain to them.
Yeah.
Because if this is right, I win a fiver. Because Triv bet against me.
Luckily, it's Monopoly money, so it's okay.
It's okay. But I'd still rather win because I want to buy Mayfair.
Don't tell Triv. Anyway, so I bet that both of these will have an elastic collision with the ground and bounce up.
Yeah. And I bet that this marble will not bounce up. It will have an inelastic collision with the ground. So it will go there and it will just stay there, or pretty much just stay there. It won't bounce very much. And I bet that the bouncy ball would have an elastic, so they'll be different, is what I bet.
Alright.
Fiver to Wayne, I think. The bouncy ball had an elastic collision, it bounced back up. The marble just hit floor and stay there.
But, Wayne, inelastic. So I imagined inelastic as something hitting something and then we're going away together, but it didn't go through the ground.
It didn't.
So how do you tell if it's an elastic or elastic collision?
That's a good question. Okay. Now, let's go through the answers. Okay. So, an elastic collision. Triv's wasn't a perfect elastic collision.
No. But elastic collisions when one, talking about bouncy ball, one hits the surface and then bounces away from it.
Yeah. Both as one particle hits another, it's going to bounce back with the same kinetic energy, so there's going to be no loss in energy and no loss in momentum, because momentum is always conserved. And
that's the thing that matters. If there's no loss in kinetic energy, it's elastic.
Yeah, that's the important part. So there'll be no sound, whereas with Trivs there was a sound because it's not a perfect world and these aren't particles. But that would be described as an inelastic collision for today.
Whereas in an inelastic, it is not conserved.
Yes, so momentum is still conserved because it always is.
It always is.
But energy is lost. So an example would be as cars collide, because of their crumple zones, they often
sort of almost fuse together and go away as one. And this would be an example of an inelastic collision. Now you've got to use these concepts and apply them to work out often the speed or the energy, or even sometimes the mass in some of your questions.
Yeah. So often, well, in your exam, they'll say that elastic collisions are particles, so they are pretty close, if not perfectly elastic. Yeah. Whereas the bouncy ball, that wasn't perfectly elastic.
That wasn't, no, because it was sound release and there was some heat somewhere.
Yeah, so really neither of us win the fiver, but it was more elastic than the marble, which is what I bet.
Yeah.
But in your exam it will be particles colliding. You'll know the masses of them, they'll tell you that. Yeah. The velocities, you can work out the reverse velocity. It would just be the same reverse if it's perfectly elastic.
Yeah.
Cars crashing, lorries crashing, stuff like that. A trolley going down a ramp, it's another trolley at the bottom, and they move along at X speed.
And you work out the changes in kinetic energy or changes in momentum between the two, and work out therefore is it elastic or inelastic, or maybe they'll start with that and you work your way backwards.
So I've got a small question. I've made it up right now.
Oh, okay, I like it.
So we've got a lorry. I'm going to draw it as a square.
It's a nice lorry.
In your exam, try and be quick and just draw squares rather than a nice detailed lorry.
You're not going to get any marks for nice bridge diagrams, just useful ones.
So there's a lorry.
There's a lorry.
I'll tell you it's travelling at, say, 50 metres per second.
That's pretty fast, but go on.
I made it up. Say it weighs 10,000 kilograms.
Wow.
Yep, it's a very heavy lorry.
It's pretty much a train, this one.
And coming up behind the lorry is a car. Okay, it's travelling at, say, 70 metres per second. So it's travelling much quicker.
Yeah.
And it only weighs 1,000 kilograms. Now, I know these numbers are a bit ridiculous, but you see what's happening.
Yeah.
Basically, there's cars on the phone, he's smoking, he's doing lots of bad things.
Bad things, things that you shouldn't do.
And he crashes into the lorry.
Oh dear.
And what we say is that it was an inelastic collision, so they're now an object, they're together. Yeah. And if I told you that after the collision they moved away at, say, 20 metres... No, I won't give you that. I won't give you the speed they move away at. What if I'm asking you the speed that they move away at?
Okay.
After they've collided into one mush of icky stuff. No one got hurt. No one got hurt.
So that's okay.
What's the velocity when it moves away? So we've done this sort of question before, but now we can explain it as an inelastic collision. That's the sort of thing you'll say. So
you can use this just using the change in momentum.
Yep. So you work out the total momentum before.
Yes, and then you work out, you add these two momentums together. Now, you should know that momentum is mv.
Yep.
So we'll have
equals mv.
70,000 plus 50, 100,000, 500,000.
50, 1, 2, 3, 4, 500,000.
Yep.
You're going to add them to, because that's the momentum of this and the momentum of this. You add them together.
Yeah, and then you divide them by the new total mass. And a new total mass, as they are together, will be 11,000.
Yeah,
which
so
isn't very nice to divide
now
by.
combined. It's now 11,000 kilograms. That's what you've got to notice. The momentum's the same as Triv said.
Yeah.
You're then going to have the momentum divided by 11.
Yeah, and that will give you the speed. Then you can work out, say, the kinetic energy, and you could do the same thing for the kinetic energy before, and you could show that it was elastic, so there would be a change between these two kinetic energies.
Exactly, that's another key thing I was going to go on to. That's the new thing. So half mv squared, what's the total?
Yeah.
Same process.
Yeah, and then you do the same thing over here, and it would be different.
So you'd have to do the momentum first to work out the velocity of the result. This is why it's like a step question. It's the sort of thing you get in your exam. Then when you know the velocity, you can do the half mv squared of this one, compare it to the kinetic energy here.
Sure, it's changed it, say it's inelastic, get an A and go home happy.
We believe in you.
Yeah, you can do that.
If you have any questions on any of this is the end of Module 1.
It is. And it may not be for your course, that's fine, but we'll answer questions on any course, provided it's physics, or maths, chemistry and biology.
And if you have any questions from any exam paper or from your book or from whatever.
Yeah, just ask it to us. Tell us what exam paper it is from, so we can check we're actually telling you the right thing.
Or send us a picture of the question if it's in a book or whatever.
Either works, and we'll get you a sort of step-by-step how to do it. This is revision, so we're not doing it as in much detail.
This is an overview.
Yep.
You can ask us in the comments below if you have a YouTube account.
Or you can go on
Google
Facebook.
Mail account. I get notified.
Or Google Plus or whatever.
Yeah.
You can go on Facebook, and you can tweet us if you're a bird.
Yep, and we'll tweet you back.
Yep.
So that's elastic and inelastic collisions. That's the momentum chapter over.
Yep. And so now we're on to something a bit more exciting.
So you're Module 2.
Ooh.